Maybe. Maybe you will. Who's to say? Okay, so processing is a chapter that I put in the notes, so sort of a theoretical aspect. There are, I think, going to be like maybe just a couple lectures in this chapter. So I'll start off with like a broad overview of what I want to accomplish in the chapter, and then we'll do lecture 1 from this chapter today. Probably next week we'll do another chapter on the stack, or another lecture on the stack, or a stack, and we'll kind of introduce that a little bit today, and you get a better feel for it. This is the level at which we interact with the processing lends itself to thinking about a stack. So we'll get there, but we have some layers in between we're going to try to build up. So a CPU has an abstract model called an instruction set architecture, or ISA, that typically describes how the processor interacts with memory, inputs, outputs, and instructions. A popular architecture for personal computing is the x86 architecture. So you guys, most of your Intel chips that you guys have interacted with, most of your laptops, most of your home PCs are x86 architecture. And they have an instruction set associated with them. So they have instructions that at the very lowest level in machine code, the processor interprets and executes in actual circuits. So that's the instruction set architecture. Is describing the instruction set are the actual instructions that you would hand in, and the architecture is how it goes about taking an instruction and moving on to the next instruction and handling it at that very low level. So for mobile and embedded computers, however, the ARM ISA is ubiquitous. So ARM, and then there's also the MIPS as well. There are a couple, but ARM is definitely dominant in mobile, and a lot of embedded stuff is ARM. The ARM instruction set architecture is a reduced instruction set computing architecture, so sometimes called RISC architecture, which means its instructions are less complex than those of a complex instruction set computing architecture, such as the x86. RISC architectures are often used in embedded computers. So different types of RISC, MIPS is another one. And specifically the embedded computing lab where we're working, the computers in there, the NIMI Rio 1900 boards, so C Appendix A1 use the ARM architecture. So I'm going to actually open that up to that appendix. Specifically, the system on a chip, Xilinx Z7010's Cortex A9 dual CPUs use the ARM version 7A instruction set architecture. So, in fact, let's just go ahead and do this. That one. Yeah. So it's this one. I'm just going to stick it over here. And we're just going to look at one page from that, from this appendix. So so Appendix A. So let's look over here. So this describes just a little bit in more detail. So it's centered around the NIMI Rio is centered around a Xilinx Z7010 system on a chip, also abbreviated SoC, which has a dual-core A9, a Cortex A9 CPU. Actually, the dash is in the wrong spot. Should be dash right there. It has memory, I/O interfaces, and an Arctic 7 fully programmable gate array, FPGA. And so you can look at the data sheet. I linked to that Xilinx data sheet. So this is a really powerful system on a chip. This thing has got not only a dual-core processor in it, but it also has an FPGA, which we don't have a lot of time to get into, but it allows us to do very specialized digital signal processing at a rapid rate. Okay, so they're not as general purpose as a CPU, these FPGAs, but they allow us to do, for instance, like input-output at a very high rate, which is really great for control, for embedded control, which is what we're trying to do. So this sort of a system on a chip is nice. It comes with a processor. I mean, this is not what's on the motherboard of your laptop. So the motherboard of your laptop probably just has a processor that's right on there, and then RAM and other things. So this is like building a lot of those things into a single chip. So processor in there and certain other components in there. And it's great for certain embedded applications. This is a really high power system on a chip. I think, so this is not something you would put into a low-end product. So you wouldn't put this into something that, so like the example is a toaster. You wouldn't want to put this in a toaster. But because I think the cost, if you want to buy, well, it depends on how many you buy. But if you want to buy a one-off one of these, they're like $50, something like that.
Just a chip.
For the system on a chip. So you're not going to put this into a really cheap product. But something that has high control performance requirements, that's a more advanced device.
Computing or this, like elevator to allocate the
Right.
elevator
That's a good example. Right. So you might use it for industrial control or some big machinery that like an elevator in a hotel or something like that has a lot of computing requirements if you're going to do it in a sort of optimal way.
The reading they use this input from the user to allocate this elevator car.
Yeah, that's a good example. So yeah, it's so this these MyRios are much more powerful than like your average embedded computer, but they are what we would use in a really sort of high power requirement case. They're pretty cool.
How about this remote control car?
Maybe a really high end one. I mean, it would be because when you're gonna put a $50 system on a chip in it, I mean, you got to be selling that car for quite a bit of money. So, yeah. They get cheaper as you buy them in bulk, obviously, but I mean, still tens of dollars per chip. So they're high powered. They have these 667 megahertz clock rates on the Cortex A9 CPUs and have single and double precision vector floating point units, which allows us to do really efficient floating point calculations. So we can do a lot of fast, efficient floating point calculations. They have these special registers that we'll talk about that they have dedicated to just doing floating point arithmetic. And then they use the ARM v7A instruction set architecture, which we'll talk a little bit about. So what they do is they build these chips, and they say, okay, every single chip. It's not like people are going to learn how to interact with every single chip if they're going to program it, like at the very lowest level. So they come up with these instruction set architectures that are all kind of similar. So the ARM ones, so ARM v7 is version 7, and then -A is a variant of it. They kind of have just different, they evolve, but sort of in the same thing. So if you learn how to do really low-level ARM programming, version 6 to version 7 to version 8, like there are some new features, but they're roughly the same. So if you learn ARM, you're probably fine. Low-level embedded computing architecture at some level, knowing how to interact with that is fine. If you're going to learn how to do very low-level stuff with an x86 architecture, like for instance, if you're going to be building very efficient application-level software that runs on a PC, or if you are interested, so that would be writing it in C and trying to get down and use the capacity of the chip at a really low level, or if you're designing an operating system that wants to operate very efficiently with the microprocessor, then you would need to worry about what architecture you're working on. But when we write in C, technically, of course, it's system independent. We can write something. It might mean something slightly different on a different chip with a different instruction set architecture, and certain things you might be able to do on a certain architecture that you can't on others, and sometimes it's just an efficiency thing. So we are kind of going to look under the covers here and see, like, okay, ARM. We're going to look into ARM a little bit, because ARM is our the one that we're going to use in the lab, and we're going to learn a little bit about how it works down there. I mean, pretty high level still, and I'll sort of show you guys like the vastness of what you can do to learn. The system is very cool, very complex, and it's worth reading some. I actually spent a little bit of time this last week reading in the reference manual and the programmer's guides for it, and I'll show those to you. So, okay, so that gives you guys a little bit of background there, and actually maybe this is a good time to show you. So the ARM, so there's like the addressing modes section, but if you look this up, this is the ARM Architecture Reference Manual, version 7A, and it's 2,700 pages long, which is intimidating. It's really intimidating, but what I have to say is that they do a pretty nice job considering the vastness of this. Like you can actually read some of this stuff with understanding, and it does a pretty good job of describing what it is to you. So you don't already have to necessarily be like an ARM expert. Like this is how you would learn to be an ARM expert, is reading through this manual. So really great sort of ARM. So all of the chips that are made with ARM architecture version 7, which is a whole lot of cell phones out there, iPads, that type of thing, pretty much all use this. There's a version 8 now that some new stuff is coming out in, but version 7 is still like most of the stuff is in version 7, and it's just an incrementally developing system. And yeah, so describes the instruction set, describes the registers, describes all kinds of stuff.
So you mean the Apple that already announced that they use A9 architecture or something like this?
So the Cortex A9 is a specific processor that uses ARM version 7 instruction set architecture. Mm-hmm. So the Cortex A9 uses this. Our processor is a Cortex A9, so it uses this. And so we can look in the ARM reference manual to understand how it works. I mean, so Cortex A9 versus another ARM chip, they might be a little bit different. Like, I mean, they might have completely different manufacturers. They might make them completely differently, but they should have the same instruction set. They should operate in the same way if you look at it from this level. If you hand it this instruction, it'll do this. If you look for a certain register, it should have that register. These things, in order for it to be an ARM v7A, it has to comply to these things. So it's sort of like I guess, industry-wide architecture that everybody complies with. And so there's that. You can look into that. There's a whole lot in there. There's a whole lot in, so the MyRio user guide and specs will explain to you that, on here we have a processor and an FPGA. This is all inside the Xilinx 7010, which is what we've got. Lots of cool stuff there. And if you wanted to look up, the Xilinx 7010, then here's just the overview data sheet. There's more to it than this too, but you can see, it says we use the ARM version 7A architecture. It's the Cortex A9 based unit, and then it has the caches and the on-chip memory and the I/O and all that. So all of these, like, there are so many layers of complexity here that we obviously can't go into all of them. We would never be able to write our programs, keypads and LCD screens, and then eventually controlling stuff, right? So we can't get into all of it, but what we can try to do is understand at some level, and usually we would call this sort of a programming model of what's happening down there. Like, what's going on down there approximately, or from some perspective, what's going on down there.
Like we press a button, how it's going to register our button, something like that?
Yeah. Well, and for now we're going to focus on, but yes, you're right. For now we're going to focus on what happens if we look for like an instruction. If we hand it an instruction, like what does it do? What's all going on down there? So we'll try to give that. I'll try to give you guys that. It's really, I have to admit, daunting to try to lecture on this material because it's so vast. This is part of why this lecture took me a while to get prepared, because I just didn't know how to bring it into some sort of form that I thought was palatable. So let's just kind of first remember this sort of simple understanding of a computer that we started this semester with, which is that a CPU has three functions that are repeated endlessly. So if they fetch instructions from memory, they translate the instruction, and then they execute it. So that's what the CPU is doing. And remember, the CPU has two aspects to it. It has the control unit. So typically the control unit fetches the instruction from memory and translates them. And then sends to the data path of the CPU to be processed. It does this by means of registers, which are small special purpose units of memory in the data path. So they're actually like onboard little places to store instructions and data. And these are very, very, so remember, we talked about these just in passing. We talked about memory. The fastest, most expensive type of memory is actually registers that are right in there in the CPU they hold like the next instruction or the next few instructions or the next few pieces of data for us to use. We can get stuff from memory and put them in the registers and then do stuff with them. Okay? And we can put stuff back in memory. So memory is something that we want to use. Remember, there's the sort of the very fast, expensive, small capacity memory that's closest to the CPU, quickest to access, read, write from. And then the further away you get, the memory gets cheaper and larger, and also usually there's this permanence to it as well. It's not a volatile memory, non-volatile memory, so it'll stay if power is lost or whatever. So we've got this sort of concept of memory that's kind of close to the processor, moving far away. And then we've got the register being sort of the ultimate little bit of memory that we can use for doing computations. So that's this really high-level view of what's going on. Let's go down and look at registers on an ARM processor in an ARM instruction set architecture. So a developer of an embedded system with a given CPU must understand it at the so-called application level, which is distinguished from the so-called system level of the operating system. So we're thinking of, how do we program this thing? Like, we assume there's already some operating system there. On our boards, it's actually a Linux-based operating system. So we assume that that's there, but we want to write an application to run on that machine. And that's what view we're going to look at. So an application level view of the ARM processor registers has 13 general purpose 32-bit registers named R0 through 12, and 3 special purpose registers named SP, LR, and PC, which you can also call, but we're not supposed to call R13 through R15. They say, like, we deprecate calling them these in the manual, but then they also say also called R13 through 15. And this is just a reference to the place in the manual that describes this. So the stack pointer, or SP register, contains the memory address of, and therefore points to, the top of the active stack. So we're going to brush against stacks for a moment, and then we'll review them later. So a stack holds data such as automatic variables temporarily, and we're going to talk more about them later. There's this concept of, like, throwing stuff on top of the stack. We'll get back to it, and then pulling stuff off the stack. So the stack pointer tells you where the top of the stack is in memory. The return link register is used, for instance, to store the current memory address of the calling program during a subroutine call. So say you call some sub function from your main, say, and it goes off and computes, like, your F gets keypad or something like that. Well, your main program that's running, you got to get back to where you were in that main program. And so that's what the return link register does. It stores that memory address of where you were in your program. So if you are, like, 3 levels deep, you might need to have references, links down to there. So it keeps track of where you are, I guess, when you go do a subroutine. A program counter PC register contains the memory address of the current instruction plus 8 bytes. So there are 8 different, so there are 8 digits, or 8 integers in between the current instruction and what the memory address held in PC is. So that is a 2 instruction from now integer. So 2 instructions is because they're 32-bit instructions, and 4 bytes holds 64 bytes, 64 integers. So you've got 2 instructions from now. Now the 2 instructions from now thing is like a legacy, apparently, due to some old stuff, but they can't really get rid of it now. It's, like, stuck in ARM. So there's a whole thing on the internet discussing it, but yeah, just knowing that that's the case is all you really need to know. You don't really need to know why it's like that, because I guess the only reason why is some old reason that doesn't matter anymore. Back when they first made ARM version 1 or whatever. So yes. So yeah, so it's approximately what the current instruction is, but it just for legacy reasons, it's actually 2 instructions from now. So, the general purpose registers, so that these are the R0 through 12, typically hold data such as ints, doubles, and chars. So it could be instructions also. So we can put stuff in there. So when we do a certain thing in the data path, so say we're going to like add 2 numbers, you're probably going to pull 2 numbers from 2 different registers. Hopefully they're in your registers. You can also pull them from memory addresses, but if you have them queued up in registers, it happens quicker. So you prefer to do things from your registers if you can. Other ARM registers. The 32-bit application status register. So these ones were all the core ARM registers. They are on every ARM system. And these other ones are not necessarily to be guaranteed on every ARM system. So this is specific to version 7a. I'm not sure which other ones have these. So the 32-bit application status register, APSR, stores the memory's last executed instruction return status in these flags. So N would be a negative condition. So, for example, a 2's complement negative most significant bit is going to be 1 if it's a negative number and 0 if it's a positive number. So if you did, for instance, an add and you got a negative number out, your negative condition bit should be 1, saying, negative result. The 0 condition, which is often something that is turned to 1 to say, they're equal. So, for instance, when you compare 2 things, are they equal? You would say the 0 bit is often flipped. You have to use these appropriately, right? So you use these in an instruction. The instructions are used. The instructions will return, like for instance, we'll set the 0 condition bit to 1 if the 2 things you're comparing are in fact equal, that type of thing. So these are sort of these are flags that can be used, and they're used often for the next instruction. So and we'll talk a little bit about that. So the carry condition, for example, an unsigned overflow from addition would say, well, we've overflowed our buffer, or we've overflowed our number of bits when we added these or whatever. We had an overflow that went beyond what we represent in the 32 bits, for instance. In which case you would set the carry condition. There's one left over. There was a carry that had to happen. You can do the same thing V, but it's preferable for signed overflow. And Q for overflow or saturation, typically from a digital signal process that you're doing. Now, these are all encoded as single bits. So when an instruction finishes, it can set any of these bits. I mean, very, very quickly, it has the capacity to do that. And then the next instruction is going to overwrite that stuff. So you gotta use it immediately, or it gets blown away by the next one. So these flags can be tested by the next instruction for conditional execution. A nibble of the APSR stores the GE flag, which is a greater than or equal flag, which is another one that you can set, but it uses 4 bits. So these are useful to do some sort of like conditional executions, like if these are equal, then do this. So one instruction executes, and then the next instruction can immediately start because it can look at that register, and it always has access to the previous instructions right to the register, to the application status register. And so one thing I didn't stress before, and that is that, yes, this is all ARM-specific stuff, but a lot of these architectures, instruction set architectures, have something like this. So if you learn ARM stuff, it's not like it has no bearing on an x86 or MIPS. They're related. They're just they can be slightly different in some aspects. Okay. These flags get okay. So the execution state registers allow special instruction sets such as thumb to be executed. So the thumb I haven't talked about really, but if you look in the manual for ARM, there are these specific sort of a smaller instruction set that's sort of a special purpose instruction set that can be used in some cases. They call it thumb. There are a few others too. There are some variants like thumb EE, and there's another one I can't remember what it's called. And they're like sort of like sub dialects of the instruction set architecture. And so this one is the execution state registers are mainly saying, do you interpret this instruction as being a thumb instruction or just a regular old ARM instruction? That's one thing that it can set. It can also contain thumb special instructions, so like some things that are very thumb specific it can contain. And it also sets the register endianness mapping, so big endian, little endian. Remember, the most significant bit happens either on the right end or the left end, we would say. And it's up to the architecture. So actually, this can change it. You can change it by changing this register's endianness mapping flag. So some other things you can do. I mean, there's just like so many possibilities. It's kind of unbelievable we actually make anything with these things. They're just like so complicated. But fortunately, we have abstraction, right? We don't have to understand every little detail of this thing to be able to program what this thing does, right? We can wrap all of it up in a layer of abstraction and then another layer of abstraction, and then like you guys have been using PCs for years and you didn't know any of this stuff. So yeah, I mean, maybe you did, I don't know. I shouldn't have said. Okay, so the Xilinx Z7010 Cortex-A9 has the optional ARMv7-A vector floating point unit, so it's called VFP version 3 ISA extension, which enables high performance and efficiency of floating point arithmetic. The extension has its own dedicated extension registers. So there's like more registers in the version of the Cortex-A9 that we have. So there are different options that you can get. This is one of them, and it gives you extra registers. So you can and these registers are dedicated to doing floating point arithmetic.
It's like our computer have different video card for processing.
Exactly.
Video.
Exactly. And actually, I didn't include it here. So this one actually has something called, in addition to having the vector floating point extension, it also has what's called Meon extension as well, which does, it's often used for encoding or decoding media files like MP3, like audio or video. So mostly audio, I think, something like MP3, for instance. So like it's dedicated to a specific task, like this sort of extension of the architecture. So it's, yeah. And now you're seeing, this is totally an aside, but you guys may have seen in the news, but like a lot of these cell phone companies are now putting out their phones not only with an ARM chip on it, but also with a dedicated AI chip. So like it's specifically built to do some AI tasks. So it could be like your OK Google sort of task of for instance, interpreting natural language. They're doing natural language processing. Same with Siri as well. So like I think a lot. My guess, and I don't know this, and I think they're kind of secretive about what they're doing actually with them. But my guess is that a lot of it's just doing natural language processing. So yeah, which is a very resource intensive thing to do, especially on a regular processor. But if you design it specifically to do that task, you can make it more efficient for that task. So yeah, it's interesting. I don't know if that's going to continue to be a trend or not, but something that's going on. And then of course you guys are familiar with like the graphics processing, GPUs. Like some gamers in the crew here that are specific to graphics and are optimized to do that sort of process. So yeah, so we've got, I mean, what we care about a lot of times for an embedded computer when we're doing control is to compute things with floating point numbers. Like we want to compute how much voltage to put out. Well, we have to multiply a bunch of numbers together and add them together and divide them, and floating point numbers are usually the easiest to work with. So we would prefer to do it that way if possible. Okay. Great. Types of instructions. So we talk about the instruction set architecture. We talk about, the registers and like what the registers do, and we're going to talk more about stacks and how the instructions are going to go through the stack and operate. But let's talk about the different types of instructions that the CPU might encounter. So we might load or store from CPU registers. So we might take something from one register, put it in another register. Or we might take something from a register, do a calculation on it, put it back in a register, put it in a different register, write it to memory. We might move pieces of information, so data from one point in memory to another point in memory. That might be something we would do. We can set or reset bits. We can shift or rotate different pieces of data. We can do arithmetic, like adding, subtracting, multiplying, dividing, making negative. We can do logic, ands, ors, etc. Conditional branches and jumps. So you might reach a point in your program where you want to go this way, do these lines in memory given a certain condition, or maybe jump past that and do these other lines in memory. So like when the compiler writes it, it doesn't know necessarily when the program reaches a certain statement, if it's conditional, which it's going to need to go, right? So you might need to skip from one point in memory when you're running your program, one instruction, the next instruction. Oh, if x equals 5, then you have to maybe skip 17 instructions to go down there. So it could do that as well. That might be an instruction to like skip 17 instructions. You can do unconditional branches and jumps too, where you just say go to this part of memory or skip these or whatever. And then subroutines, so like a function. So instructions, there are several, ARM instructions, the idea of having a reduced instruction set architecture is that you have instructions that are less complex. Each one is less complex. Doesn't mean you can't do very complex things. It just means that each instruction doesn't have as much to it. Honestly, there's no clear distinction between a reduced instruction set versus not, but people still love labeling them So they do. I mean, like even in the ARM thing, it says this is a reduced instruction set computing architecture. And yeah, but also 2,700 pages. It's not like so much that the number of instructions is smaller. It's just that each instruction is supposedly more compact, or there's not as much to it, each instruction. Yeah.
I was going to use a jump command in our last lab, but when I was looking it up, I think it's like jump 2 in C.
Mm-hmm.
They were saying like the jump command is like really lazy programming, and like it makes it hard to read. Like, you shouldn't use jumps.
Yeah.
Unless it's like absolutely like what's your...
There's a famous paper that I think like, because people used to use them a lot in programming. So there's a very famous paper that was written by, I can't remember, I think it was like it was a famous computer scientist, and it's called Goto Considered Harmful. So Goto statement is another type of jump statement. So like go to line 14. And so the paper is called Goto Considered Harmful. And I think, I mean, the main point was you never have to use it. And even when it seems like it's going to be helpful, it makes it almost impossible to read what somebody did, or to predict. When you look at the program, it's hard to predict how it's going to execute. If you can at least say it's going to execute down these lines and it's not going to suddenly jump up to line 17, you can at least have that to fall back on when you try to decode what's going on. And it's never necessary. So I think it's a style thing, but there are a lot of people who think it's very bad form to use them. I don't know. I'm always on the fence about a lot of these things. I'm like, okay. Like, it's considered harmful, like, yeah. But also sometimes I don't feel like maybe writing this in a different way. So
if you jump, I mean that the line of code that we want to skip, it will not execute it, and it will execute directly jump to this line.
Yeah, so you could be on line 20, for instance, and you could say, like, if this go to line 14, and then it'll just stop executing, and it won't do 21. It'll go to 14 and it'll execute down again, and then
even further.
It'll go back to that statement if you go up. So if you go back up, for instance, then it'll encounter that line again. So if it's just a simple unconditional like go to, it'll just keep going back, right? Just be an infinite loop. But you can also make it be conditional, and then you could have it like go up and then, oh, see, like now it's fine, and keep going. So we do stuff like that where we repeat things, but we would explicitly write a loop for it most of the time.
Can it skip forward?
It can also skip forward, yeah. And you can also skip to other scripts, so other function, other files. So like you could go to line 7 of this other file. So it's really, I mean,
It sounds like a while loop.
I mean, you can do it. And you can use it as a while loop. I mean, it's very flexible. And I think that when people first started programming with it, they were like, yeah, I mean, it's great, like all kinds of flexibility. But I think it is really hard to follow what's going on. If it gets complicated, like if you have one go-to over to here and then you have another one over to there, and then you're like, okay, wait, so like when does this thing make this jump? And then what happens when it comes back to this point? It's really hard to follow. So typically you can write anything. I believe you can write everything without using them. And if you want to, like, for instance, jump back up and keep doing the same thing, like, that's just a loop. And writing it as a loop explicitly, like, while this or for this, makes it a lot easier to figure out what's going on. And it also, I think compilers do a lot better with it, too, because then when they compile the code, they don't have to decode the go-tos as much. So yeah, it's not something you can't use. It's something that is just discouraged. And I don't know. I've
Because I think
whatever.
he asked during our second lab is that when we type the input more than the buffer length,
Mm-hmm.
it will just have some bugs. For example, if you call it twice, it will just send this overflow to the next one.
Right.
Something like this. That's why when we type over the buffer length, it will just skip these things, not to overflow. So we don't return enough files.
Yeah. Yeah. There are, I mean, one of the things that I think is hard for people learning computing is that there are so many options. Like, you can do things in so many ways. And I think that oftentimes until you see a programming problem that's open-ended, you've really been, like, there is an algorithm handed to you for how to solve every problem that you've encountered. And then when you get a programming problem where it just says, like, construct this, or like you could do it with this type of loop or that type of loop or with a bunch of conditional statements, and it's a challenge. So yeah, and then like I don't want to restrict you and say like you never use it. Some people think you should never use it. I'm pretty agnostic about it. Okay. So another thing that in instruction set architecture describes is addressing modes. So addressing modes specify how the CPU is to calculate the memory address for a load or a store operation. So for the ARM version 7A ISA, the address is composed of two parts, a base register value and an offset. The base register can be any core ARM register, so R0 through 12, or a stack pointer, or program counter, or whatever the other one was. I forget that one. Link. Yeah, so it can be any of those. The offset must have one of the following three formats. So it can be either immediate, an unsigned number, if it's immediate. It can be summed with or subtracted from the value of the base register. So that would be the format of the first type of format for an offset. The second format for an offset is register, and that format is a value from a core ARM register other than the program counter. So you can't use the program counter for that. And then the final format for an offset is the scaled register, which is a shifted value from a core ARM register other than the program counter, summed with or subtracted from the value of the base register. So those are the three formats the offset can take. These lead to the following three addressing modes. Offset addressing mode. In this, the offset is summed with or subtracted from the base register, forming the memory address. So when you guys say things like, what is the address of this piece of data by using the ampersand operator in C, you guys are looking at an integer, right, in hex 0, 0, blah, 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 right? This is what we're looking at. When down at the processor level, this is how it constructs. This is how it deals with the memory address, okay? So offset is the first type of addressing mode. Another one is pre-index. So it's the same as offset, followed by the new address being assigned to the base register. So being. And then post-indexed, the memory address is the value of the base register, then the base register is offset. So these are just different modes for constructing an address for some piece of memory inside the processor. And they're useful for different things. So pre-index and post-index can be useful for a bunch of sequences that come like one then the next and then the next. And a lot of this stuff comes down to having these different modes. You might think, well, why make it more complicated? Why not just have one way to do things? A lot of times what it is they're eking out some sort of efficiency from this machine. I mean, you want to have this thing perform different types of operations. This thing is a very general purpose. Remember, it's doing completely different things. Sometimes it's doing arithmetic, sometimes it's doing logical things, sometimes it's doing all kinds of different stuff with this data. And sometimes it's more efficient to use these different addressing modes for different types of situations. So that's why it has these options in case you need to use them. So we are just trying to get like an idea of how it works down there. We're not going to be too worried about this most of the time, right? Like we're not like even writing, like we're not writing the machine code that says like set this bit to a 1. That's usually not what we're doing. Usually we're operating on some higher level of abstraction with C. But occasionally, you're going to want to understand how it's working down at that level. And C gives you the types of things that you need to get down there. So for instance, like the address concept, memory address, which isn't, to my knowledge, even a concept in MATLAB or Python. Maybe you can do it. I've never seen anybody use that, at least in MATLAB or Python. That's not the level at which those languages interact with the machine. So we can get down there, we can get things like what is a memory address for this, flipping bits and that type of thing. But oftentimes we won't do that. Sometimes we do something like this. We think about it in terms of these operations just so we can eke out some efficiency, recognizing like, oh, if we do it this way in C, it'll be more efficient than if we did it this way, because of this way of this architecture using addressing modes. That would be an insight we would only understand if we understood the architecture a little bit, at some sort of high-level understanding. Clearly, we aren't going to understand it at the 2,700 page level. We're going to understand it at like we've skimmed a few sections level, and we understand roughly what's going on. We understand that there are registers. We understand that when it operates through a program, it's taking one instruction, then the next instruction. And we will have to deal with an abstraction that I'll talk about next time called a stack, where we have a pile of instructions that we throw up on there, and then we take them off the stack and execute them. So we'll talk about that. We will encounter things that we need to write in our programs that deal with like a stack, for instance. So we'll come back to that. Hopefully this has been a little bit enlightening. I think this is probably the hardest subject I've ever tried to construct a lecture on. So it's just so vast. So hopefully that is helpful. And then we can do something more practical now.